Sorry, Dimitri. Got it. Yeah, that's good.
Oh, good catch. First, I would like to acknowledge the traditional owners of Australian land and pay my respects to the elders past and present, acknowledge the Bunurong people. Today, I'm happy to present Miguel Ugeda, a Ikerbasque research professor at Donostia International Physics Center at San Sebastian in Spain. He's one of the leaders in the physics of strongly correlated phases in novel monolayer materials, including superconductivity, excitonic condensation, and magnetism. Miguel received his PhD in 2011 in the Universidad Autónoma de Madrid in Spain, and after a postdoctoral position at the University of California at Berkeley and Lawrence Berkeley National Lab, he returned to the San Sebastian as a research fellow at CAC Nanagan and Centro de Física de Materials, and in 2018, Miguel moved to the International Physics Center, where he is a research professor now. Okay, Miguel, feel free to start. The stage is yours, and we will enjoy the talk.
Okay, so you hear me, right? So good afternoon, everyone. First of all, of course, let me thank the organizers, Dimitri, Victor, Susan, and Michael for their kind invitation to participate in this colloquium series. I'm so glad to be here today. Well, as you can see from the title of my talk, today I would like to tell you about two-dimensional heavy fermion system, which is in particular a two-dimensional Kondo lattice that takes place or it's realized in a simple bilayer of transition metal dichalcogenides, which is sort of unexpected, as I will show you in a second. But first of all, what do we understand by a Kondo lattice? A Kondo lattice is anything else but a periodic array of individual spins, which are what? Which are immersed in a pool of conduction electrons with which they do interact. So this apparently simple problem has fascinated many generations of condensed matter physicists. And the reason is because the interactions of the spins mediated by the conduction electrons are not full, or the mechanisms are not fully yet understood. So today in this talk, I will show you that this simple bilayer, heterobilayer, is the practical realization of a two-dimensional Kondo lattice, where the 1T polytype of tantalum diselenide hosts the isolated magnetic moments, whereas the 1H phase of tantalum diselenide is responsible for providing the pool of conduction electrons. Okay, so what's the significance of all of this? Well, even when the physics related to electron correlations is very rich, and it's known for decades, in general, all this phenomenology has been observed or has to be sought in very complex materials, in general bulk materials, three-dimensional materials, where the particular electronic or magnetic properties of the material are highly dependent on the stoichiometry or in the quality of the samples, etc., etc. So the fact that transition metal dichalcogenides host electron correlated phenomenon is a very good news, right? Because it provides a simple and accessible platform for to study all these phenomena, but also, and more importantly, because it adds a new dimension to study this phenomena, which in general, in the past, has been only possible to do in 3 dimensions. Okay, having said this, this is the outline of the talk. Today, I would like to tell you about the 1T over 1H phase of tantalum diselenide, which behaves as a coherent two-dimensional Kondo lattice, as I said. But first of all, I would like to give you a short introduction about the two main roles in this combination, which is the 1H phase of tantalum diselenide, which behaves on a metallic substrate, and the 1T phase, which hosts, as I said, the isolated magnetic moments. Okay, but before doing so, and now that I'm talking to people really far from here, let me spend a couple of minutes introducing the group. So we are a small experimental group located here in San Sebastián. San Sebastián is a small town, a small city here in the north of Spain, very close to the border with France. You see it here in the north. It's a beautiful city, actually. If you don't know it, I do recommend you to visit us because it's a beautiful city with 3 beautiful beaches, and the food is very good, and the science as well. In particular, in comparison with the size of the city, there are many different scientific institutions. So for either for tourism or for scientific reasons, I do recommend you to visit us. Okay, so as I said, we are an experimental group. We call ourselves 2D SPM group. And the main focus of our activity is basically to do research on unusual collective electronic phenomena that arise in novel low-dimensional materials, mostly 2-dimensional materials, with a particular focus on superconductivity, even when today I will not talk about superconductivity. Well, I will talk about like 5 minutes, but this is one of the research projects in which superconductivity is not the main thing. So the methodology, we use molecular beam epitaxy and scanning tunneling microscopy. So here you have a picture of our homemade molecular beam epitaxy, in which, this is where everything starts, right? Because here's where we grow all our 2-dimensional materials. This is a system which is particularly designed to grow only selenium-based 2D materials in order to avoid any cross-contamination. So we only grow TMDs or at least selenium-based materials. But once we have grown these materials, we basically cut them and take them in general to many other characterization regions. And of course, we've been able to grow very different 2D TMD materials, such as, for example, superconductors, transit wave materials, but also semiconductors, even ferroelectric materials. But we can go beyond these materials. For example, I will show you today that we've been able to grow 2-dimensional TMD alloys, mixing, for example, 2 different transition metal elements. And also we can grow heterostructures, vertical heterostructures, such as the one I'm going to focus today, the 1T over 1H, or 2-dimensional lateral heterostructures. Today I will show you results about 2D materials, TMD alloys, and vertical heterostructures. So let me show you one STM image of a lateral heterostructure. Here you have 1T titanium diselenide embed in an or with a nylon embed of 1T niobium diselenide, which is a mud insulator system. Okay. So once we have grown these materials, our main tool for the structural, electronic, and magnetic characterization is this STM system that you see here that operates in ultra-high vacuum conditions at the base temperature of 340 millikelvin, and we have the possibility to apply out-of-plane magnetic fields up to 11 Tesla. Cool. So let me get started with this system. Let me give you some words about the 1H system, the 1H tantalum diselenide layer. Okay, so the electronic structure of the 1H tantalum diselenide phase is dominated by only one single band that crosses the Fermi level and provides the metallic character to this material. So as I said, this band has a D character coming from the tantalum atoms. And the only peculiarity about this band is the fact that it's a spin splitted around the K point due to the strong spin orbit coupling. It's a non-magnetic material. We have done some experiments that I will not show today to prove that this material is not magnetic down to 2 Kelvin. And another characteristic of this material in the single layer is that it holds a charge density wave order below 130 Kelvin, in which the STM is very good at detecting these charge density waves. because in addition to the atomic registry, you can see a clear 3x3 pattern that corresponds to the challenged wave. Okay, so here I show you a DADB curve taken.
Could I interrupt you for a short
sure.
question? Could you return to the previous slide?
Yep.
Could you tell us where the chemical potential Fermi level in this material is just?
It's here. This one, 0.
Oh, it says respect to the Fermi level. Oh, I see.
No, 0 is the Fermi level.
Mm-hmm.
Yeah. Did that answer to your question?
Mm-hmm. Yeah, thank you.
Okay. So 0 is the Fermi level, yes. So I'm showing you here a DADB spectrum taken on single layer tantalum diselenide, where you can see, well, let me clarify that DADB is something proportional to the local density of states, right? For those who are not familiar with tantalum spectroscopy, DADB signal is, proportional to the density of states, to the local density of states. So I'm showing you here a typical DADB curve taken on tantalum diselenide H phase. So the shaded region is the part that corresponds to the D band. Okay, in particular, this prominent peak you see here, this shallow peak as well belongs to this part. This is the Fermi level here. So it's a normal metal at 300 millikelvin. But interestingly, if we zoom out in this region, okay, close to the Fermi level, we see the emergence of one deep in the density of states around the Fermi level with a width of about 8 milli-electron volts. So the origin of this deep is not entirely clear. Several groups have attempted to attribute it to different things in the past. For example, it's been attributed to a heavy fermion gap, also a challenged wave gap in this material. So it's not clear exactly what the origin of this dip. I would say personally that it's a challenged wave gap, but I don't have smoking gun evidence about it. But what is interesting is that inside this dip, there is another one, a clear additional dip with a width of 1 milli-electron volt. That could be a superconducting gap. Okay, at least it's compatible with incomplete, not a hard gap, but it could be a superconducting gap. So whether this material is superconducting or not at 300 millikelvin is something that we looked at in the past, right? Okay, so here I show you 3 different curves taken with the same tip and the same location on the sample for at 0 Tesla, at 3 Tesla, and at 5 Tesla. And as you can see, however, they basically lay in the same or are identical to each other, and therefore we can rule out that this peak to be related to superconductivity. This is interesting because tantalum diselenide turns out not to be a superconductor at 300 millikelvin, and the behavior in the behavior of superconductivity in this type of materials, in this type of TMDs versus dimensionality, shows a quite distinct character. For example, the niobium family of TMD materials show a decrease in the critical temperature, or I mean, superconductivity is weakened with the number of layers. In the case of niobium disulfide, actually disappears. Superconductivity is not sustained in the single layer form. In the case of niobium diselenide, it's a bit weakened, but it survives in between 2 and 3 Kelvin. For the case of tantalum-based TMD materials, the behavior is actually disparate. Whereas for tantalum disulfide, it has been reported an increase of the critical temperature, a reinforcement of superconductivity with the number of layers. Whereas for tantalum diselenide, it shows the opposite trend. So this superconductivity disappears as well, at least at 300 millikelvin. So it's not clear what these trends are not clear, or there is no picture that explains this disparate behavior in this family of materials. Okay, but if you look carefully at the band structure, actually there is a trick to induce superconductivity in tantalum diselenite. So if you look at this particular region between K and gamma point, you will see that one of the spin split bands is very close to the Fermi level. It's very close to the Fermi level, so we are very close to a saddle point at the Fermi level, which is obviously or represents a logarithmic divergence in the density of states. So perhaps if we add a minute electron doping in the system, we will be able to reach this Van 't Hoff singularity, enhance the density of states, and therefore to trigger superconductivity. So this is something that we tested, or we try to do in the lab. And how did we do that? We did that using a chemical doping. So if you look at the chemical the periodic table, I'm sorry, tungsten is next to tantalum, and it is an isoelectronic element, and the only difference is that it adds one electron to the system. So basically, adding or substituting tungsten by tantalum provides extra electrons to the system, and therefore we can electron dope it, right? So what we did was to grow this alloy, which is basically tantalum diselenide, but with some percentage, a dilute concentration of tungsten. So we did this experiment in between 0 and 7%. So the way we can identify the tungsten atoms basically is so this is the fingerprint of a tungsten atom in the tantalum plane, because even when we see the selenium atoms, because we are on top there, we see triangular features that reflect the fact that the 3 selenium atoms bonded to the tungsten have a different density of states, and therefore they are different from the rest of the selenium atoms. And here we can count individual atoms, 1, 2, 3, 4, and that's how we can estimate the overall concentration of tungsten. So here I'm showing you the magnetic field dependence and the temperature.
Miguel,
Yes,
could I interrupt you again?
sure.
Could you return to the previous slide?
Yep.
Except in addition to the bright triangles, you have, for instance, the black ones. Or use
The what?
I would say the black.
The black. Oh, these ones. Yes. Well, this could be other types of defects. Yes, vacancies, or we don't know exactly what kind of defects. But they are not, I think, related to tungsten. In particular, one of for example, these 2 black triangles are pointing in the opposite directions to the bright triangles. And so if they are substituting, if these are so the fact that they are pointing in the opposite direction means that whatever it is, that defect is not a substitutional tantalum atom, right? Because otherwise it should be oriented towards one of the directions, cannot point in 2 directions. Do you follow me?
Yes.
So probably the black ones are, I don't know, I don't know what kind of defects, selenium vacancies, tantalum vacancies, I don't know, but
some features look like lines. For instance, in the bottom right, they're not just one, but they
bottom right here.
Oh yes, they're not like one defect. It looks like deformed lines. Is there any physics behind this?
Well, so in addition to the triangular bright features, you have to keep in mind that we are looking at the transit wave as well.
Oh, I see.
So yeah, so probably what you identify as a sort of defect is probably the contribution actually to the transit wave.
Okay, thank you.
Yeah. Okay, so here I show you the spectroscopy for one of these samples. In case, it's 2.5% of tungsten atoms, right? So this is the magnetic field dependence, and this is the temperature field dependence. So as before, we also see a dip at the Fermi level, center around the Fermi level, with a width of like 0.5 milli-electron volt or so. But in this occasion, the dip responds to the magnetic field. So if we increase the magnetic field, basically the width and the depth of this dip, it varies up to 0.75 per Tesla, in which basically remains constant. So if we normalize all these curves to the upper curve, where we observe no variation, basically a clear superconducting gap emerges here, right? So here's the evolution of the superconducting gap, and this is something that we can fit using the standard VCS superconductivity. So here I show you the evolution of the gap with the magnetic field, and the same here for the temperature dependence. So at 300 millikelvin, basically we see a dip that evolves with temperature becoming narrower and narrower and less shallower and shallower. We do the same normalization, and basically we can extract the gap as a function of the critical temperature. So we can extract the upper critical field and the critical temperature for a particular concentration of tungsten atoms. So if we do that for different concentrations, basically we can end up building the phase diagram for this material, where we see a dome, a superconducting dome that spans between close to 0 up to 3% of tungsten doping. Basically, this is a dome with a maximal critical temperature of about 1 Kelvin, right? And basically, this dome reflects the shape of the density, the shape of the density of states when we go from one side to the other side in the Van Hoff singularity, right? Okay, but unless you do this trick, the system is metallic, is not magnetic, and it's not superconducting. So this is the substrate that we have. Let me now just give you some introduction.
Could I interrupt you again?
Sure.
Since it is two-dimensional material, is it supposed to be this type 2 superconductor?
It is a type 2 superconductor, yes.
It's 2 critical magnetic fields.
Yeah, we have not studied the first one.
Vortices and etc.
We have not seen vortices. We have not seen vortices. Well, no, we have not looked for them.
I see.
Yeah, at least for this work. So in order to extract the lower critical field, you need to do that. But it's very time consuming, and we decided not to do it at least for this experiment.
Okay, thank you.
Yeah. Yeah, as I said, let me give you some words about the 1T phase. And first of all, let me explain why do we have, or why this polytype of tantalum diselenide that applies as well to niobium sulfides, etc., other types of 1T phases in TMD materials, why they host isolated magnetic moments. And the reason behind it is that these materials at low temperatures undergo a charge density wave, which is called the Star of David for obvious reasons. And below this critical temperature, basically the material rearranges in a super lattice like this, where there is a central atom, and the 12 tantalum atoms surrounded undergo an elastic deformation going towards a central atom like this. Okay. So this is something that can be easily detected in STM as well. You can see here the central atom and the 12 surrounding atoms around it. Okay. So what's so special about the charge density wave? So the charge density wave, this charge density wave, basically, so there are 13 atoms in the new supercell. Okay, so that means that so each of the tantalum atoms contributes to this supercell with one electron. And therefore, if you carry out the band structure of this material, basically there are the formation of 13 bands, 13 new bands. 12 of them are filled here, okay? And now they are spatially located in the surroundings of the Star of David. But there is one lone electron that is supposed to live or to be localized at the center of the Star of David, in which there's one band, basically. There's one band with only one, which is half filled, with only one electron localized at the center of the Star of David. Okay, so that is the origin of the isolated magnetic moments, right? So we have one electron basically localized at the center of the Star of David, holding one half of a magneton, and therefore that's, so we can think of it as the an array of magnetic moments. And actually, if we now add correlation effects, basically the energy cost to put a second electron at the center of the Star of David, basically this half-filled band splits into two, right? And therefore, this material in principle is a mod insulator material with one subband totally full and one subband totally empty. But both of them, and this is important, should share the same orbital texture and should be localized here at the center of the Star of David. And that's an important detail, as I will show you in a second. Okay, so the question is, what is the ground state of this periodic array of spins? Are they, for example, in a ferromagnetic pattern? Are they showing a more complex antiferromagnetic pattern? Well, it's not clear yet what's the ground state of this array of spins. So it's been proposed recently, a couple of years ago, by the group of Kondo, that this system is a good candidate for being a quantum spin liquid. So quantum spin liquid basically is it's a phase of matter formed by an array of interacting spins, but disordered. Therefore, there is no long-range magnetic order, but instead it shows long-range quantum entanglement and other properties such as the charge fractionalization. It's a many-body system. It's a very exotic state of matter. So, and the reason that support this claim is that in this material, when it's grown on graphene, basically they observe a supermodulation that they ascribe to the existence of espinon Fermi instability. So an espinon is basically an excitation of this ground state. It's basically, you can see it as an isolated spin that it's able to diffuse in the quantum spin liquid, right? So that has this diffusion has some signatures at the Fermi surface, which you see here. I'm not going to get into details, but basically, in principle, this is the fingerprint of the quantum spin Hall phase. So in our opinion, this proposal is very interesting, although it has some fundamental problems, and the reason is because we have also done a spectroscopy on tantalum diselenide when it's grown on graphene. So the key point here is the graphene. So here I show you a color scaled set of DIDV curves in a color code, okay, along this path, okay. So we go through 1, 2, and 3 Star of Davids from here to here, and you can see that basically the system shows a hard gap. Okay, so there's a hard gap of around 0.2 electron volts, and this is the valence band. Here, this is the conduction band. They show they are in opposite phase. Okay, when this sharp resonance is visible, then the conduction band is basically gone, and vice versa. But the point here is that are these two the lower Hubbard band and the upper Hubbard band of a mod insulator that enables the formation of a quantum spin Hall liquid. I'm sorry, a quantum spin liquid. So in order to be a quantum spin liquid, it has to be a Mott insulator, right? And therefore there will be one isolated spin in each of the star of Davids. So this is what we put into questions, because if you resolve the you spatially resolve the extension of this band, the valence band and the conduction band, basically they show that they basically are localized in different locations. So the valence band is localized at the center of the star of David, as expected for the Mott insulator, but the conduction band is systematically, or the intensity of the conduction band is not located at the star of David, but in the outer part of the star of David. This is not consistent with a Mott insulator, and it's only consistent with a simple band insulator. So we are carrying out DFT calculations in order to disentangle this problem, because basically if we had a Mott insulator and we have now correlations, basically we would have something like this, and this is compatible with the existence of magnetic moments. But if for whatever reason there is some electron doping from the substrate, in this case graphene, to the 1T phase of tantalum dichalcogenide, basically the band would be filled, and therefore would be no correlations and no isolated magnetic moments, and therefore the system would be a simple band insulator. So this is something that we are still carrying out and investigating. But okay. Having said this, the situation, by the way, as I will show you in a second, is totally different when you substitute graphene by the H phase. And this is what I want to show you now. Okay.
Miguel, could I interrupt you again?
Sure.
Does this spin liquid picture assumes that you have very strong antiferromagnetic interactions because it is triangle lattice and the system is in frustration regime?
Yes.
Is it obvious that interaction is antiferromagnetic between individual spins?
No. Well, actually, no. The spin order is not clear at all. XMCD experiments have been carried out in this layer by the group of Micromi, and they have not detected any sort of magnetic order. So that's something that in principle supports the idea that it's a quantum spin liquid as well. But whether we have that or an antiferromagnetic order, of course, the one-by-one antiferromagnetic order is not possible because what you said, it's frustrated. But they could show other more complex spin textures which are compatible with antiferromagnetism.
This picture requires that interactions between neighbor spheres is antiferromagnetics, that they tend to have the opposite directions.
Yeah. Yes. And I will show you in a second why this is possible, in particular in T and over H phase, mediated by the substrate.
Okay, I see. Thank you.
Yeah. So here I show you a large-scale STM image where you can see the typical morphology of our samples. This is basically, I think it's 1 micron by 1 micron, where you can see that after the growth, basically the tantalum dichalcogenide grows in islands, large islands around 200 nanometers. You can see that for this particular coverage, the second layer starts to grow. So in most of the cases, these first layers that are next to, there are basically on top of graphene are H phase. So this is the metallic phase. In most of the cases, this is the H phase. But so you can see that these monolayers are usually decorated by other patches forming the second layer. So if you look carefully at these second patches, in many occasions, you see that these triangular features are is the 1T phase of tantalum dichalcogenide. So basically, there you have the heterostructure, the bilayer, 1T phase, and the H phase underneath. So this is where we have done our experiments.
Sorry,
Okay,
can I ask Miguel, Do you do anything with the growth to change between the phases, or is it just a natural preference for one T growing on top of one H?
So you have to play a little bit with the temperature. Yeah, right. I didn't mention that. I think in tantalum diselenide it's relatively easy to get the 1T phase, whereas, for example, in niobium diselenide is really hard. So you have to go to really high temperatures in order to have the T phase. In tantalum diselenide it's easier, but yet you have to go to slightly higher temperatures during the growth.
Yeah.
The temperature of the substrate in order to get a significant fraction of the T phase. So yes, this.
Thank you.
But yeah, so once you get this kind of sample, basically you can look at these bilayers. And here I show you a typical DIDB spectrum taken on in one of these bilayers. Let me remind you that DIDB is something proportional to the local density of states. So basically we observe 3 different peaks, 2 broad ones and a sharp one at the Fermi level. So in this occasion, we identified these 2 broad peaks as the lower Haber band and the upper Haber band. And the reason is twofold. First of all, because we have done conductance maps at these energies, right? At 80 millielectron volts, which corresponds to the maxima of this peak, and at 130 millielectron volts, the maxima of this peak. And basically, the conductance map is telling us where basically the wave function associated to these resonances is located. In this case, unlike in the case of tantalum diselenide on graphene, the maximum of the intensity is located at the center of the Star of David, which is what we expected for the upper Haber band and lower Haber band. So if we take this energy difference as an effective Haber repulsion, it gives a number of 200 millielectron volts, which is inconsistent, or it's very close to the value theoretically calculated, not for tantalum diselenide, but for niobium diselenide and tantalum disulfide. So we do believe that these 2 bands are the upper and lower Haber band. In particular, because also we see a sharp resonance at the Fermi level, which basically coincides with the fingerprint of a single moment Kondo. Basically, we have 2 states. This is one impurity state. This is the impurity state plus the Coulomb repulsion, and basically a sharp resonance, which is the fingerprint of a single ion Kondo due to virtual transitions undergone in order to screen this isolated magnetic moment. So this has been observed in the past in 1T1H, different 1T1H phases, for example, in tantalum diselenide, in tantalum disulfide, tantalum diselenide, etc., etc. So this is something well established, and actually people have studied the width with the temperature in order to make sure that this is a Kondo feature. So nothing new. So the motivation for us was to try to unveil what's the ground state of this system, right? Because okay, so we have a Kondo lattice. These isolated magnetic moments are screened by the conduction electrons. But what happens if we go lower and lower in temperature? What's the ground state of these 2D Kondo lattice? So according to the Doniak phase diagram, which was developed in the 70s, if you continue to lower down the temperature in a Kondo lattice, different ground states can show up depending on the strength of the interaction or the coupling between the magnetic moments and the conduction electrons. So depending on the strength, so for example, if the strength of this coupling is relatively weak, then the system will prefer to go or to show a magnetic order, or to show a magnetic order with some spin interactions mediated by the substrate, in our RKKY interactions. However, if we continue to increase this coupling, and for a certain critical value, basically the system prefers to become a paramagnet and all these spins will be fully screened by the conduction electrons, which is called the Kondo insulator regime. So what we have done is to study these two grounded states in terms of the density of states, which is what we measure, right, with STM. So here I show you a picture of what in terms of the Kondo insulator in the band structure. So the origin of the Kondo insulator regime is the interaction between the localized, the flat band due to the localized magnetic moments, which is depicted here in green, and the interaction with the conduction band electrons, which is this dispersive band. So the hybridization between these two bands lead to new spin-degenerated bands, both above the Fermi level and below the Fermi level, creating which is called a hybridization gap here, close to the Fermi level. In the magnetic order ground state, the situation is relatively similar. So there is one hybridization of the bands, but in this case, the magnetic order leads to the formation of bands, of spin polarized bands, in the conduction band and in the valence band. So basically, and forms a magnetic gap as well, as you can see here. So in terms of the magnetic field, and in the absence of magnetic field, the situation is really similar, and it's a bit ambiguous in order to distinguish between these two grounded states, right? However, there is a key difference between these two band structures, which is that in the Kondo insulator regime, we have spin-degenerated band structures, whereas in the magnetic order state, we have spin-split bands. So if we apply a magnetic field, in principle, these peaks should split into two here in the conduction band and in the valence band, whereas in the magnetic order case, there should be just one displacement, relative displacement between the peaks due to the Zeeman effect, but no new structure should show up. So there's one way to distinguish between these two ground states. So this is what I did. Here I'm showing you again the DIDV at 4 Kelvin. So if we now cool down to 300 millikelvin, which is the base of our STM setup, basically we observe, as expected, the split of this Kondo resonance into two peaks with an average distance between the peaks of 1 milli-electron volt. Okay, so this is something that is expected. But it's important because even when we don't know exactly which is the ground state, what is for sure is that we have reached the coherence of the system. Okay, so the Kondo lattice is not behaving as isolated magnetic moments surrounded by the pool of electrons, but there is a new ground state, which is a many-body state which involves all the spins at once. Okay, so we have, of course, carried out the temperature dependence. Here I show you a set of curves taken in this in the same location, where we increase the we increase the temperature from 300 millikelvin up to close to 4 Kelvin. You can see that of course the resolution gets worse and worse, and basically there is a moment at which we are unable to resolve these two peaks. But the interesting thing is that the distance between the peaks basically does not vary with the temperature, and basically we believe that probably the coherence of the spin lattice likely occurs at temperatures larger than 4 Kelvin, and the only reason why we don't see it is because of the only reason why we don't see it at 4 Kelvin is because of the limited energy resolution at 4 Kelvin, which is about 1 milli-electron volt. Okay, so we have also studied the spatial extension associated to these two peaks. Okay, so in particular in this region where you see some Sadov-Davids, we have done conductance maps at -1 milli-electron volt, plus 1 milli-electron volt. You can see that in both cases, basically the conductance is pretty much identical. So the intensity of the conductance is mostly focused on a triangular shape, has a triangular shape with some secondary spots here, which basically reflect these three atoms, selenium atoms, which means that we are, or these two states basically are located at the central atom of the Star of David. And the reason why we see this triangular feature is because, as I said before, we are looking at this selenium atom, so therefore we see a triangle, okay? But this is as expected, localized at the center of the Star of David. Obviously, we have carried out the magnetic field dependence. Here I show you another set taken with the same tip in the same location from 0 Tesla up to 11 Tesla, where you can see that basically nothing changes except for the distance between the two peaks, right? At 0 Tesla, it's around 1 milli-electron volts, whereas at 11 Tesla, it's around 5 milli-electron volts, a little bit less than 5 milli-electron volts. So there's a gradual separation of the peaks, but anything else. Here I show you all the curves overlaid so that you can see that basically there are no new features except for this gradual separation. In this set, you can, which was taken with much higher resolution, you can see that the peaks behave similarly, and basically there are no new features showing up for large magnetic fields. So there are no emergent features in the density of states with the magnetic field, and therefore we are in a good position to rule out the possibility that we are looking at a Kondo insulator regime, right? Because of this, because basically we should observe a splitting of these peaks if it was a Kondo insulator system. So the only compatible possibility is the magnetic order. So there is something else that we have learned from the magnetic field dependence. So here I'm showing you a plot of delta. Delta is, let me remind you that delta is the separation between the two peaks as a function of the magnetic field. Here we can distinguish two different regimes. The first regime is happening for magnetic fields larger than 0.5 Tesla or so, where we see a strict linear dependence of these two peaks, which basically, of course, we ascribe to the Siemens splitting. But interestingly, for magnetic fields below 0.5 Tesla, the system is highly non-linear. So here I show you a zoom of this particular set of data, where you can see that basically below 0.5 Tesla, the system leaves the linear dependence. So this gray band that you see here is the error band that we calculate in the whole regime. So this displacement is totally real, and it ends up like 200 microelectron volts below where it should be. So, however, this distance is pretty small. It's typically 1 or 200 milli-electron volts. So in order to make sure that, or in order to convince ourselves that it's true, we basically repeated this experiment, which basically one of these sets takes usually 1 day. So, and if you have to be lucky because the tip should not change. So we repeated this experiment in 35 or 36 different Star of Davids to convince ourselves that this shift is actually real. Here you have the final histogram, and you can see that basically this nonlinearity is around 100, 200 microelectron volts. So it's small, but it's real. Another possibility could be that the coil that we have in the STM should give not a linear response, but we are sure that this is not the case, and these non-linearities of the coil can be excluded. And the reason is because we have measured a totally different behavior, an opposite behavior in clusters using the same tip. So here I show you an example. You have two clusters in which we have repeated the experiment. And in this cluster one, the trend is going upwards, but with this slope, whereas in the cluster next to it, the tendency is basically going upwards, but the slope is different. So we can exclude any instrumental artifact. So one more thing we have learned about it is that the magnetic field. So we have changed the polarity of the magnetic field while doing the experiment, and we basically have learned that basically all we see is basically symmetric with respect to the 0 Tesla, and there is no hysteresis or any other no symmetric behavior with the polarity of the magnetic field. Okay, so once we have gathered all this information, basically, okay, the gradual separation of the peaks is compatible with the magnetic order. The fact that we see no emergent features in the density of states is also compatible with the magnetic order. So the question that still open is whether this nonlinear behavior and the symmetric evolution of the separation of the peaks is also compatible with the magnetic order. So at this stage, we carried out a minimal model using a mean field calculation that was carried out by Fernando de Juan here, which is excellent theorist here at the DAPC. Basically, he carried out this calculation in which to take into account the interaction between the isolated magnetic moments and the conduction band electrons. So basically, this is the Hamiltonian that he used, and he basically calculated the density of states of the system assuming different magnetic orders. So here's the expression for the separation between the peaks. Okay, so it has two terms. Basically, one that takes into account the strength of the coupling between the magnetic moments and the conduction electrons, and is proportional as well to the magnetization of the conduction electrons due to the magnetic field. Okay, and the second term is just proportional to the Siemens splitting. Okay, so as I said, here we plot the density of states using this calculation for in-plane magnetic order and an out-of-plane magnetic order. So in the case, regardless of the particular type of magnetic order, if the magnetic order is in plane, basically the density of states that we should expect looks like this, with a minimal distance between these two peaks at 0 Tesla, increasing gradually for both polarities. Okay, because we are basically counting the spins in both directions in the same way. So basically, everything has to be symmetric with respect to the 0 field. However, if we have an out-of-plane component in the magnetic order, basically we should observe one polarity in which these two peaks are separate each other, whereas for the opposite polarity, these two peaks should get closer and closer and closer and eventually merge in one single peak at one particular finite magnetic field. This is not what we observe, and therefore we can rule out any out-of-plane magnetic order or any out-of-plane component in a potential magnetic order of this system. But this minimal model can also capture the non-linearities that we observe in the separation of the peaks at low fields. And the reason is because of this first term, in which basically we take into account this the magnetization of the conduction electrons, right? So there are two terms. When the magnetic field is large, basically this second term dominates, and the system is just linear. But when we have small magnetic fields, this first term is also important and basically leads to different behaviors depending on the particular magnetization of the system, which is exactly what we see. Okay, before I finish, let me just give you one more argument why we are not in the Kondo insulator regime. We can make some numbers to estimate, for example, the strength coupling of the isolated magnetic moments with respect to conduction electrons. This is this expression, which is basically proportional to the hybridization between the flat band and the conduction band. over the Coulomb repulsion. And this number can be extracted from the ab initio calculations, which has been therefore fitted using tight binding calculations. So we can extract a hybridization energy of 20 milli-electron volts. The Coulomb repulsion was estimated by the STS results, giving a estimation for the strength coupling of 15 milli-electron volts. If we now compare this number to the critical coupling strength needed to go to the Kondo insulator regime, basically this critical coupling is, if you look at the literature, is inverse to the bandwidth. It's exactly inverse to the bandwidth. And basically the bandwidth of this band is basically this one. This is the half of milli-electron volt, and therefore the critical coupling strength has to be like 250 milli-electron volts. So according to these little numbers, so we should be here depth in the magnetic order part of the Doniak phase diagram. So this is the end of this talk. We've been able to grow these heterobilayers, which act as a two-dimensional Kondo lattice. The electronic structure and behavior with the magnetic field allow us to rule out a Kondo insulator ground state. And basically, this behavior is only compatible with magnetic order, which is mediated by RKKY interactions. So, of course, we have not done direct measurements of magnetism, but this is something that, as you can imagine, we are carrying out in the lab right now. We want to learn more about possible magnetic order emerging in these particular materials, and this is something that an ongoing project in the lab. Okay. With this, let me just thank you, my collaborators. First of all, let me thank the people involved in this and in this work, Wen-Wan and Paul Dreher, who basically took most of the measurements that you have seen today. From the theoretical side, we have counted with support by Fernando Juan here at the DAPC, Maya Garcia Berniori and her student, Irian Sanchez, and the DFT calculations that you have seen were done by Antonella Menino in the group of Ion Herrera. And with this, let me just thank you for your attention. If I have like 30 seconds, let me advertise a conference that will be carried out here in San Sebastian about novel 2D materials, basically explored with scanning probe microscopy and spectroscopy. You can check out the details of the conference that will take place this next June here in San Sebastian. So please check out the details and come to visit us. And with this, let me just thank you all for your attention.
Thank you. First of all, let's thank you, Miguel, for fantastic talk.
Wow. Thank you to you.
And welcome to questions. Please just go ahead and ask. Do you have any questions?
Hi, Dimitri. I have a question. I don't know.
Hi, Hussein.
Hi, very nice talk. Can you hear me?
Yep.
Yep, perfectly.
Actually, yeah, I was going to ask about those spin resolved STM plans you have. What kind of technique are you envisioning?
Well, it's been of course,
planning some ESR or any chromium tip or
the regular spin polarized experiments with chromium tips, exactly.
Oh, okay.
Yeah, it's taken us a bit longer than expected, and the reason is because in particular I've never done spin resolved measurements, so you know that these experiments in order to calibrate the tip are a bit tricky, and it takes a lot of time. But yeah.
Okay. Yeah. Thank you. Very nice. Look forward to seeing those results. Thank you.
Any other questions? Please just go ahead.
I have to say, by the way, that it's possible that we see nothing. depending on the particular arrangement, we may not see any signal in the spin resolve STS measurements. So
Yeah, there's always a chance, right?
exactly.
Well, good luck.
I have another question. So if your ordering is in plane, so if you have strong enough magnetic field, it start to polarize all spins. And if magnetic field increase some critical value, all spins will be out of plane. Is it how large this magnetic field could be? And it's probably there are some estimations based on these calculations of series that you have presented. And if it's any trend to this, if it have been observed or...
So you're talking about the
Yes.
so if we apply out of plane, basically with 11 Tesla, your question is if we have
at some point, do you expect some saturation when all spins will be pointed out of plane?
So there's no way for us to distinguish this saturation, I would say, because all we measured is the distance between the peaks, which is and the reason is which is a Zeeman effect. So whether these spins are saturated or are aligned with the magnetic field or not, that's something that we don't know. We don't know exactly. So probably spin resolve measurements will shed some light on about it, probably, of course.
Okay, I see. Thank you. And other questions, please just go ahead and ask. It's a bit unusual. Okay. Any other questions?
It's too late over there.
Maybe can I ask another question, Miguel?
Sure.
Yeah, sorry. So you had those nice diagrams, those band structures where you distinguish the Kondo insulator with the magnetically order phased, right? You have two bands. So I'm not sure I understand what those bands are, or how to reconcile that with your, there's two bands on the left, right? Yeah, I don't know if you can elaborate on that.
So you mean this one or this one? So this is just on a sketch, I have to say. The real situation in this particular problem is way more complicated than this, and the reason is because there is no only one band, but 13 bands involved. Okay, so this is a simplified sketch, assuming one flat band and one conduction band. So there are 13 bands involved here, and of course the same applies to the magnetic order. But regardless on how complex the system is, these are features that basically can be observed in always. The hybridization.
Yeah. So if I understand correctly, you have the conduction band from the metallic substrate, and then the flat bands are the localized impurities. Is that?
So the flat band comes from the isolated magnetic moments, which is called a heavy fermion band, right? And the conduction electron is provided by the H phase. Yeah,
I see, the underlying metal. Okay.
Yeah.
Yeah, thanks. It's pretty clear. Okay, thank you.
Yeah, I have another question. So you argue that you're far away from Kondo insulator regime, but
according to the estimation, yes.
But if you imagine that if you're close to it, you have these two bands that hybridize, this wide conduction bands and narrow valence bands. What symmetries do they have? So I'm asking if you could get the topological Kondo insulator, like samarium hexaboride, if it would be the case. So in samarium, one band is I don't know, D, another band is F, and because they have different parities, when you have hybridization, it's supposed to have some phase winding, and the resulting band structure in this
Yeah.
mean field theory becomes topological.
Yeah, so I cannot respond to your question to what happens exactly if we were close to the critical point, but let me mention that, of course, I simplified the picture of the Doniak phase diagram because the Doniak phase diagram looks like this, actually a bit, let me show you. Yeah. So this is a more realistic Doniak phase diagram where you have the magnetic order, you have the Kondo paramagnet, but there is a critical point which is not just a point in which in between you have magnetism, but it's sort of screened as well by the conduction electrons. So we believe that we may be probably living here, but the critical point, it's not a critical point exactly. It's a mixture between the Kondo paramagnet and the magnetic order.
Okay, I see.
Right.
Life is more complicated.
So, your question about topology, something that I cannot respond. Actually, I'm not familiar enough to give you an accurate response, but so I wanted to clarify about the critical point, which is a bit more complicated than a single critical point.
Okay, unless we have any other questions. If not, let's thank you the speaker again.
Okay, thank you so much for the invitation.
Yeah, and yeah, bye to everyone, and see you next year. I think we will have a large break, so see you in March.
Nice to meet you.
Okay. Thank you.
Bye, everyone.
Bye.
Stop recording.